scalar product today. There's some other names. Sometimes it's called the dot product or the inner product. And all it is sort of the rule for multiplying two vectors. We've learned the rule for adding two vectors. It's really easy. You just add corresponding components. The rule for multiplying vectors, although we don't call it multiplying vectors, we call it the scalar product, is you multiply corresponding coordinates and then you add those results together. And you can do it in 2 dimensions or in 3 dimensions, but because we get just a number in the end, that's part of the reason it's called a scalar product, because a scalar is just a number. So what does that look like? Well, if you have 2 dimensions and our first vector is 2, -3, and we're doing the dot product with 1, 2. Go back just quickly. So if we were going to do the dot product between these two, all we would do is 2 times 1, which is equal to 2, -3 times 2, which is -6, and add those together, and our dot product would be -4. For our second example, if you go to 3 dimensions, our first vector is 2, -5, 3, dot product with 4, 1, -7. 2 times 4 is 8, -5 times 1 is a -5, and then 3 times -7 is -21. Adding those together, -26 plus 8, -18. So the mathematics behind it is relatively straightforward. It's not a hard thing to calculate. But there are some properties from scalar products, and then there's some very interesting things that happen. The scalar product, if we look at it, whether in 2 dimensions or 3 dimensions, it doesn't matter the order. U dot V is the same as V dot U. So that acts the same as other numbers and stuff that we've worked with. If you have a constant out in front, you could put that constant with your first vector, or you could put that constant with your second vector. Dot product is distributive. So if you're adding 2 vectors inside and you have a dot product out in front, you could do the dot product with the first one, distributing like this, and then dot product with the second one. Or you could just add them up first together and then do the dot product. And the dot product with any 0 vector is going to be 0, because the 0 vector is the vector with all zeros. So these 4 things are basically the same as every other math thing that you've done, and so they're nothing new here. But some interesting things that happen is that when you do the dot product of a vector and itself, you will always get the length of the vector squared. Now that should make sense, because if I took the vector 3, 4, and we should know that the length of that vector is going to be 5 because it's a 3, 4, 5 triangle. But if I multiply it by itself, can you see that you'll get 3 squared plus 4 squared? Which the length of it will be the square root of 3 squared plus 4 squared. And so the dot product of its own vector is the length of the vector squared. But the most important result, put 3 asterisks beside this, is that the dot product of 2 vectors happens to equal the length of U times the length of V times by the cos of the angle between them. So this is going to save us a ton of time as far as taking our old mathematics and what we used to have to do with our old mathematics. This is where vectors is going to be much more efficient. Okay? But we'll look at some examples with this. So the dot product is always equal to the length of one vector times the length of the other vector times by the angle, cos of the angle between them. So if you know this, if the dot product is the length of u times length of v times cos of theta, you know that cos of 90 degrees is 0. And so that means if your dot product is 0, you already know that those two vectors are perpendicular to each other. Anytime your dot product is greater than 0, in other words, if cos is greater than 0, that means that angle's in quadrant 1. And then your dot product will be positive. If your angle is in quadrant 2, cos is negative in quadrant 2. And so if your dot product is negative, you already know you have an obtuse angle between them rather than an acute angle. And when two vectors are parallel, then the angle between them would be 0 degrees. And since cos of 0 is equal to 1, then your dot product is just the length of v times the length of w, or the two lengths multiplied together. So anytime we want to calculate an angle between two vectors, and this is where vector math saves us a ton of time compared to our Cartesian math before, it's just going to rearrange that formula, and it's going to be your dot product divided by your lengths of u and lengths of v. So we start off with a 3-dimension one. Maybe I'll just show you a 2-dimension one of how it works. You don't have to write this down, but then you can think back to your math that you could have done in grade 10 and grade 11 and how much work it might have been. So let's say I take, here's 2 dimensions. I'm going to take 5, 2 as one vector and 3, 7 as another vector, and you're asked to find this angle between them. If you were using grade 10 and grade 11 math, you would have to do a squared plus b squared equals c squared to get this length. A squared plus b squared equals c squared to get that length. Then you would also have to figure out the length between those, and then you could use your cosine law. Cosine law says z squared equals x squared plus y squared minus 2xy cos theta. Pretty short formula to remember, right? That's how you would do this. So how many calculations did I just mention for figuring out the angle between them? We had to figure out 3a squared plus b squared equals c squared, or 3 distance formulas. And then you had to use your cos law and rearrange it. What does it say with vectors? With vectors it says, well, I know that this vector is 5, 2. I know that this vector is 3, 7. Cos of theta is going to be the dot product, which is going to be 15 plus 14, 29, over the length of this one, which is the square root of 58, and the length of this one, square root of 29. Do cos inverse of that in your calculator, boom, you've got your angle. So it is much, much faster. So I'd like you to try this one, okay? I'd like you to try this one, this idea, in 3 dimensions, which is even if you try to do your old math of finding lengths between 3-dimensional things and trying to figure out an angle between 2 vectors in 3 dimensions, that would be really long and complicated using our old techniques, plus really hard to draw on paper. Now, with this scalar product, it makes it really easy. All right, how did you do? So if we I got some calculations separate here. Here's my dot product. When I put it together, I got 12. Here are my lengths. And so cos of theta will be 12 over the square root of 14 times the square root of 21. When you do cos inverse of that, you're going to get 45.6 to 3 sig figs. Do you remember remember what the word orthogonal meant? Right, it's another fancy word for perpendicular. So perpendicular wasn't bad enough. They had to think of something else that was complicated and didn't make sense with anything. So this also means 90 degrees. What do we know about vectors and 90 degrees? Cos of 90 degrees is equal to 0. So if we're thinking about our dot product formula, if this is equal to 0, my whole right side of my formula will equal 0. So if I know that, I now know that u dot v has to equal 0. And if I take my vectors, and this vector is 2m m8 dot, and this vector is 1 3m minus 1, and that has to equal 0. If I multiply this out, I'm going to get 2m plus 3m squared minus 8 equals 0. If we can factor this, then we can get two values of m. Either m is equal to 2/3 or m is equal to -4. Very typical type of IB question where they take an idea and then you have to use that idea to solve for a new variable. Did I make a mistake in my, oh yeah, I did. I've got to put the 2, thank you, my factoring here. Need the 2 here and the 4 there. Outside is 6, inside is 4, minus will be there. So we'll get 4/3 and minus 2. So I didn't do something that I always say I try to do, which is after I factor to do a quick check to make sure that it actually was right. And that time I didn't. I made a mistake. Ready? So if u is 4, -3, give a vector that is parallel to you. So there would be tons of possibilities. In fact, any number multiplied in front would give something that's parallel. So if you chose k to be 2, you could write 8 -6. If you chose k to be 100, you could write 400 -300. Anything that's a multiple of the vector will cause it to be in the same direction. You could even do a -1. It'll be in the same direction, but it'll be in the opposite direction, but the same, it'll still be parallel. Something that's not parallel, well, as long as you could change the first one and not the second one, or as long as it's not a multiple of the first one, it's not going to be parallel. Now, if you need something to be perpendicular or orthogonal to 4, -3, how did we do that with slopes? Because one thing I want you to think about is if 4, -3 is your vector, then your slope of this one is -3/4. Because your slope is your rise, which is your y, divided by your run, which is your x. And so if my x is 4 and my y is -3, then my slope is going to be -3/4. What do you know about slopes of perpendicular lines? what did you have to do to the slope? You had to flip it and make it negative. So if our original one was negative 3, 4, negative 3, if I flip that and make the fraction a negative, I'm going to get something orthogonal because the slope of this line, or that position vector, is 4 over 3. So it's the same kind of ideas that you've used in grade 10 math with perpendicular lines, except we changed the word to orthogonal and we switched the slope around. Whew, complicated. So we've got two vectors. Our first vector is 2x. Our second vector is 1, negative 3. If they're parallel, then 1, negative 3 has to equal k times, or maybe I'll do it just so my numbers. And it doesn't matter which one you put with the k, but I want my k to work out really easily. Yes? The x is the y in the slope. Yeah. Yeah, it's kind of nice use of letters. So the x here represents how far that vector moves in the y direction. Can you see that k has to equal 2 for those to be equal? Because if we multiply the k inside here, we'd have k and minus 3k. And so our x values would have to equal the same, so k has to be 2. And if k is 2, then we find out that x has to be negative 6. If they're perpendicular, then 2 over x would equal the flip and negative of the other one with some value of k in front. This means that 2 would have to equal 3k and x would have to equal k. From here, it's easy to see that k would equal 2/3, so that makes x equal to 2/3. Again, if you want to check this after you're done, so if we look at our 2, now one vector would be 2, 2/3. If you do rise over run for your slope here, 2/3 over 2 is the same as 2/6 or 1/3. And if we do rise over run for our other one, which was 1, negative 3, then our slope would be 3 over 1. Are these two slopes? Oops, sorry, I forgot the negative here. Are those two slopes negative reciprocals? Yes. So you can do a check after you solve it. Did it actually work out that my slopes are negative reciprocals? And in this case, they do. So you'll know that they're perpendicular. So given that these two vectors are perpendicular, in 3 dimensions, find the value of t. So our vector v is 3t plus 1, 1, and negative 1. Our vector w is t plus 3, 3, and negative 2. Now, we don't really have a thing for slope, per se, in the same way that we had previously. But what do we know about two vectors that are perpendicular? Their dot product is equal to 0. So if their dot product is equal to 0, so I'm going to write here v dot w. That would be our x coordinates multiplied together, our y coordinates multiplied together, and our z coordinates multiplied together. Everything added up, and we know that that's equal to 0. So I'll get 3t squared plus 10t plus 3 plus 3 plus 2. Or 3t squared plus 10t plus 8. Trying to factor this. Does it factor? Plus 4 and plus 2 makes 6. Yeah, there we go. Outside is 6, inside is 4. That makes 10. So that means t is negative 2, or t is negative 4/3. With that idea, I want to also go back to the question that we just did and use the other idea for figuring out b. So if you know that they're perpendicular, then the dot product would equal 0. So I'm going to erase what we did because we used slopes and the negative reciprocal the first time. Now, if we use the dot product, then v dot w is 2 over x dot 1 negative 3. That has to equal 0, so I'd have 2 minus 3x. Solving for this, we get x equals 2/3. And I think that's an even simpler way of solving for it than what we did. So seeing that again for the second time, using the dot product, for example, 6, would have probably been a better strategy. But both ideas work.